We now look at this example involving logic gates, in which we are to implement a 3-input NAND operation using the invert gate and the OR gate. So first and foremost, we observe that a 3-input invert operation can be represented with a NAND gate with 3 inputs, A, B, C, and this is our output Y. And the next thing we can best do is to represent this operation using a Boolean expression. We see that Y is equals to A, B, C, bar. What we learned when we are applying De Morgan's theorem is that we notice that we normally say that break the line and change the sign, and we say that this can be represented as Y is equals to A bar or B bar or C bar. And therefore what that means is that this is an OR operation and this is an invert operation. And therefore for that reason we can now say that this operation can be, or this expression can be written as A is being inverted. So we had A here goes through an inverter, comes out as A bar. Same thing with B bar. And same finally, always make sure that these lines are touching the gate C bar. Then once we have done that, we can take this through a 3-input OR gate, which we normally draw as such. And therefore this is an OR gate, our Y, and these are being ORed. So we have simply done what we are being asked to implement a 3-input NAND operation using an inverter and an OR gate, because this is an OR gate and these are 3 inverters, what are also called 3 NOT gates. So as you have seen, this is what we have implemented, this is what we had, this is what we have got, or as required by the example. We have another example here that says that obtain the truth table of the logic circuit given below. So what we need to do is to observe what the inputs are and then determine what the outputs are. The best way we can do that, either we can do that manually or just write down the Boolean expression that represents this gate. And this is rather simple. We can say this is A and this is A, B, B, and C. So when it gets out of here, it is coming out of a NAND gate. So we can say that Y1 is equals to A, B, bar, because that is a NAND operation. So the input Y4 is simply A, Y1 bar. But we know what Y1 is. Therefore, this becomes A, B bar, bar. Okay, that becomes our Y4. We ask ourselves what is Y2. Y2 is B, C bar. This is our Y2 because this is B, this is C, the NAND operation becomes bar. And what is Y4 or Y3? Y3 is Y1, Y2 bar, which we can represent as A, B bar dot B, C bar bar, because this is a NAND operation. So this is what we had here. So which again we can now represent, and finally our Y is given by Y4 dot Y3 bar, which we can now say is Y4 is A dot A B bar bar dot all this, then you put your final bar right there. So now that we have that, we can simply say, you can simplify this further using the De Morgan's theorem. We start with the innermost to the outermost, or vice versa, the outermost bar, and then we get to the innermost, so that if we break this line, you change this sign. You break this line, change this sign. You break this line, you change this sign. We would have Y is equals to, and before I even break this line, I would observe that this line is this. These are two lines at the same place. So these are double lines that go cancel each other. Before I even break this line, these are two lines that cancel each other. So what we have is simply A. I will first of all like to clear that up. Let me clear all the reds. So this is what we had. And I think I will only break the first line. I'll break this line and form a sign there. So what I will have is that this cancels with that. We are left with A dot A B bar, or this cancels with that. We are left with A B bar dot B C bar. So that we can now break this one and have a plus sign there, break our plus sign there, break our plus sign there. That we have that, we have that, we have that. We have A bar plus A B bar plus A bar B bar plus A bar C bar plus B bar B bar, and finally plus B bar C bar. So going further, this goes to 0. If you factor out this B, you have y is equals to, factor this out, you have B bar A or A bar plus, factor out what? This and this, you have B bar, you have 1 or C bar, then you are left with this plus A bar C bar. This becomes 1, this becomes 1. We end up with B bar or B bar or A bar C bar. Finally, this becomes B bar or A bar C bar. Quite a lengthy process, but that is our y. We will obtain that we have y is equals to B bar or A bar C bar. So we have our A, B, C, and Y. So these are the 8 possible combinations of our variables A, B, C. And since we know this to be our expression for Y, we can get our truth table to be 0 or 0 and 0 is a 1. Why? Because 0 and a 0 is a 1 and a 1 becomes a 1. This table can you just fill it because we are simply doing y is equals to what we have here. So if you have 0, 0, 1, b is b bar, b was 0, so b bar is 1, so we have 1, or a bar is 1, so a1, a bar 1 bar is 0, a is 0, and therefore a bar is 1. Dot C is 1, therefore C bar is 0. So this becomes 0, this becomes 1. That's why we have 1 here. So you do the same thing for all that, and you end up with this table that says 0, 1, 1, 0, 1, 1, 0, 0. And this becomes the truth table of our given circle. And this is what we have right there. So this is the answer you are looking for. There we get.